Hey guys. So this third problem deals with position, velocity, and acceleration, and we're looking at a velocity curve. And it may be helpful to remember that we have position, velocity, and acceleration, where position is our function, velocity is the derivative of position, and acceleration is the derivative of velocity. And so during what time intervals is the acceleration of the car positive? If our acceleration is positive, and we're looking at a velocity graph, so if acceleration is going to be positive, then the velocity is going to be increasing. So, yeah, that's right. That just happened. So if we're looking at a picture of the velocity graph, and we want to know when is the acceleration positive, well, it's when is the velocity increasing. So from 0 to 35, the velocity is increasing. Our velocity is decreasing from 30 to 45, so the acceleration would be negative. And then from 45 to 50, the velocity is increasing, so that acceleration is going to be positive again. So remember that the slope is positive if the function is increasing. So the acceleration is going to be positive if the velocity is increasing. So the acceleration is greater than 0 on 0 to 35 and 45 to 50 because the velocity is increasing. All right, the average acceleration, the average rate of change from 0 to 50. If we started off here and we ended up here, we want to try and find the slope of that line. So B is going to be the velocity at 50 minus the velocity at 0 over 50 minus 0, which is 72 minus 0 over 50, 72 over 50. My units are going to be feet per second, so feet per second, so feet per second squared. Because my y values, my output values, were measured in feet per second, and my input values were measured in seconds. So we have feet per second squared. At 40. So 40 is here. And it says find one approximation. We can really find a couple approximations, so long as that in our interval 40 is contained. So I always go on the outsides and I say, well, what would the slope be between those 2 points? And that's what I use for my approximation. So, whoa. So the acceleration at 40 would be equal to 60 minus 81 over 45 minus 35. And again, it didn't say units here, but I'm going to throw them in there. So feet per second squared. And D. Approximate 0 to 50, V of t, dt. And I want to use a midpoint Riemann sum with 5 intervals. So I'm going to have 1, 2, 3, 4, 5. If I want to go to 0 to 50 using 5 equal subdivisions, well, then each one's going to be 10. So I've got 10, 10, 10, 10, 10. In my midpoints, I like how some people are drawing arrows or whatever they got to do. You can circle them if you want. But we're going to be using those y values that are between 0 and 10. So the y value at 5, the y value at 15, the output value at 25, 35, and 45. So this is equal to 10 times 12 plus 30 plus 70 plus 81 plus 60. And then what is this? If we take the definite integral of velocity, well then this, we could either use the word displacement or we could say it's the change of position of the car. So 0 to 50, v of t dt is the change of position of the car in feet from t is equal to 0 to t is equal to 50 seconds. Okay, so there's that problem. Again, another short one. I think if we take them one at a time, it's probably a little bit better. And I'll do the last one in the next video.